Okay guys, so today we're going to talk about composition of regular and inverse trig functions. So I want to start with an example. Suppose we want to evaluate the expression tangent of cosine inverse of negative 6 over 7. I want you to first of all notice that this is a composition of regular and inverse trig functions. Composition, if you've forgotten, just means that one function is stuffed inside of another. So that's kind of what's happening here. We have an inverse cosine function, but that is being stuffed inside of a tangent function. And really what this means is the following. It means you take the inverse cosine of this number here, negative 6 over 7. That will produce some angle, and then you take the tangent of that angle. So again, let's just make sure this makes sense. Cosine inverse of negative 6 over 7, remember that the inverse trig functions produce what kind of output? They produce an angle. So therefore, this object here, whatever it is, it must be some angle. I don't know what it is, but let's just say it's some angle theta. And then we're taking the tangent of that angle. And that makes sense because the regular trig functions accept angles as an input. So just, sort of checking that the inputs and outputs make sense. All right, now how in the world are you supposed to evaluate this thing? The key idea really with all of these composition of trig functions is to always sort of start on the inside. Okay, look at the inner expression that you have and kind of ask yourself, what kind of an object is it? As I've already mentioned, this inside expression, the inverse cosine negative 6 over 7, that is an angle because that is the type of output that the inverse trig functions produce. So this is some angle theta. Now, if negative 6 over 7 were a unit circle value that I recognized, for example, if it was 1/2 or root 3 over 2 or root 2 over 2, then perhaps I could tell you what theta actually is. But negative 6 over 7 is not a value that appears anywhere on the unit circle. I have no idea what the inverse cosine of negative 6 over 7 is. All I can tell you is that this angle theta is an angle whose cosine is negative 6 over 7. That's really all that I know about this object. I don't know what theta is. Okay? Now, interestingly, you don't have to figure out what theta is in order to find the tangent of theta. Sort of surprising, but true. So how do we solve this problem? What we do really is we draw a picture. Okay? I'm going to draw the angle theta. Even though I don't know exactly what theta is, I'm going to draw a sketch. And basically, I'll make a right triangle and do some Pythagorean theorem stuff, and that's mostly all there is to it. Now let's just think carefully about what quadrant theta is in. Okay? So what do I know about this angle theta? Well, first of all, I know that its cosine is negative 6 over 7. That means that the x-coordinate associated with this angle is a negative number. That means that that the angle theta must be somewhere over here. Okay? If the cosine of this angle is negative, then theta must be over here somewhere, either in the second or the third quadrants. Okay? But I also know that the inverse cosine function has a restricted range. Remember from last time, the restricted range of the inverse cosine function, it was in radians, 0 to pi. That is, the first and second quadrants, right? From 0 to pi is this right here. So this angle theta, because inverse cosine must produce an angle in this interval, I also know that this angle must be up here somewhere, either the first or the second quadrant. Now those two conditions combined, the fact that the cosine is negative means that it's over here in the second or third quadrant, and the fact that the inverse cosine function only produces angles in this interval means that the only possibility is that theta is actually in the second quadrant. That's the only quadrant which meets both of these conditions simultaneously. So theta is somewhere over there. Now, what do we do with this information? Well, we draw a circle, okay? And now take a look at what we really know here. We know that the cosine of this angle is negative 6 over 7. We'll just recall what is the definition of the cosine. It's x over r, isn't it? Comparing these two expressions, we know, or we can see, that x should be negative 6 and r, the radius of the circle, should be 7. Now, x, of course, refers to the x-coordinate of this intersection point. So I know that the x-coordinate of that intersection point is -6. I don't know what the y-coordinate is. I'll find out in a moment. But I also know that the radius, that is the distance from the origin right here, this thing right here, is 7. Okay? Now, I do the usual thing. I make a right triangle. Okay? I make a right triangle, and as far as why I make a right triangle, let's just see ultimately what I'm trying to do. I'm trying to find the tangent of theta, right? What is the tangent of theta? What's the definition? Well, it's y over x, isn't it? We already know x. We just observed that x is -6. All that we're missing is y. And y, of course, refers to the y-coordinate of this intersection point. So if we can find the y-coordinate of this intersection point, we're done. Now, how do you do it? We've done this before. Basically, it's right triangle stuff, Pythagorean theorem. We've already observed that this hypotenuse here is 7. The length of this side, of course, is 6. Or sorry, no, it's not. That's y. That's the unknown side, isn't it? The height. Okay? This side right here, that's 6 units long because the x-coordinate of this point is -6. So if we do the Pythagorean theorem, we have y squared plus 6 squared is equal to 7 squared, or y squared plus 36 is equal to 49, which means y squared is equal to 13, which means that y is equal to plus or minus root 13. Should it be plus or should it be minus? I mean, you'll notice that the y-coordinate of this point is surely positive because it's above the x-axis. So it should actually just be root 13, not negative root 13. Now that we know y, we can actually answer the question. The tangent of this angle theta is y over x. Well, we know what y is now. It's root 13. So therefore, y over x is root 13 over x, which we said was -6. So root 13 over -6. You can write the minus sign anywhere you want in a fraction. Maybe you'd prefer to write it this way. It's a bit unconventional to have the negative sign in the denominator, but not wrong. Okay, so that's the tangent. Right? All right, let's do one more example of this kind of problem. Let's consider something like the following. Let's find the sine of the inverse tangent of -2/3. Okay? So again, this is a composition of trig functions. One trig function is stuffed inside of another. It's actually an inverse trig function stuffed inside of a regular trig function. The way that I recommend that you analyze these is always start by looking at the inside expression. Ask yourself, what kind of an object is that? Well, this is an inverse trig function, and inverse trig functions produce what kind of object? Angles. So this object here on the inside must be some angle theta. Again, I don't know what theta is, but it really doesn't matter. As we saw last time, you actually don't need to know what theta is in order to find its sine, surprisingly. Okay, so what do I know about this angle theta? This is an angle. I mean, it's not just any angle, right? It's an angle whose tangent is what? This number right here is -2/3, right? All right, so just like before, I'm going to draw a picture. So I want to draw theta, but I want to put theta in the correct quadrant. So where is theta? Like, what quadrant is it in? Well, as before, there's kind of two pieces of information. One thing is this angle theta, its tangent is a negative number. Okay, well, where is the tangent function negative? Not here, because both y and x are positive in that quadrant. So y over x would be positive. But here, one coordinate, namely the y value, is positive, and the other coordinate, the x value, is negative. So the fraction y over x, which is what tangent is, would be negative. So tangent's negative in this quadrant. Similarly, it's positive in this third quadrant, and it's negative in the fourth quadrant. Okay? So, one second. So the fact that tangent is a negative value tells you that this angle is either here or it's here. That's where the tangent is negative. But that's not the only piece of information we have, because the inverse tangent function has a restricted range. Remember that the inverse tangent function can only produce angles in the interval -π/2 to π/2. That's this quadrant and this quadrant. Okay, so we have two conditions. Tangent being negative means it's either here or here, second or fourth, and inverse tangent restriction means that this angle is either here or here. The overlap of those two constraints is that theta is actually down here. Theta has to be in the fourth quadrant. All right, so this is theta. Maybe we'll draw a circle, okay, like usual. So what are we looking for, really? We want to find the sine of theta. Well, the sine of theta, remember the definition, it's y over r, right? So I need to know y and I need to know r. Well, I know that the tangent of this angle is negative 2/3. And what's the meaning of tangent? It's y over x, isn't it? Okay, so if you compare these two expressions, it seems like y is negative 2 and x is 3. So how do I put that into my diagram? Well, y and x refer to the y-coordinate and x-coordinate of this intersection point right here. So the coordinates of this point must be, okay, so 3 is x and y is negative 2. Right? So that's my x and that's my y. Now, of course, to evaluate sine of theta, I need to know y over r. I already know what y is. I just have to figure out what r is. Well, r, of course, is the radius of this circle, which we can, as usual, figure out by drawing a right triangle and using the Pythagorean theorem. The length of this side is, of course, 3, because that's the x-coordinate of this point. The y-coordinate here, or the length of that side of the triangle is 2. So, and this side here would be r. So I know that 3 squared plus 2 squared is equal to r squared. That's 9 plus 4 is 13, so I get r squared is equal to 13, so root 13. Strange that I got root 13 again, it's just a coincidence. I suppose you could technically argue that when I take the square root, it should be plus or minus, but in context, we know that r means the radius of the circle, so it really should be plus root 13. So going back up to here, we're now ready to say what the sine of theta is. Well, it's y over r. We already knew that y was negative 2, right, from this consideration. But now we know what r is. R is root 13, so over root 13. One thing you should get in the habit of doing is always ask yourself, is my final answer the correct sign? As in, my final answer here is negative. Is that really right? Should it be negative? Well, given the fact that theta is in this quadrant, the sine of theta definitely should be negative because the, y over r, the y-coordinate should be negative. So always kind of get in the habit of double-checking that. Okay, so that's two examples of composition of trig functions. I want to look at a couple of other ones, a little different from that. I would consider these perhaps the typical examples of composition of trig functions, but there are some interesting ones. Let's consider sine of sine inverse of 1/3. Okay, so this is similar to the previous problems, except both the inverse and the regular trig functions are both sine functions. It's inverse sine and regular sine, as opposed to previously they were sort of mixed trig functions. You could treat this in the same way that we did before. You could say, oh, that's some angle. I don't know what it is. It's an angle theta. It's an angle theta whose sine is 1/3, right? And then you could sort of draw a triangle. If you think about it, there's no need to draw a triangle, all right? Like this expression on the inside is some angle theta. And what do we know about this angle theta? This thing is an angle. So this object right here, this angle theta, this object right here is an angle whose sine is what? Is 1/3, right? We certainly know that. Well, what are you doing to this angle theta? You're taking the sine of it. Well, that's going to give you 1/3, right? I mean, by definition, this angle here is an angle whose sine is 1/3. So by definition, if you take the sine of that, you're going to get 1/3. This is not shocking because you would expect regular sine and inverse sine to somehow kind of cancel out. That's typical of inverse and regular functions, right? When you compose them, they sort of undo each other. So not surprising that you just get 1/3. You could draw the triangle and the circle and everything like we did before, but you just get 1/3. But now I want to show you something rather strange. Okay, one more example. This is the last one I'll do. Very similar. Let's consider the inverse sine of the sine of 97 degrees. So I'm switching to degrees here. It makes it a bit easier. This is once again the composition of a regular and inverse trig function. And just like before, they're both sine functions. What makes this different from the previous problem, and actually from all of the previous problems, is that now the inverse function, the inverse sine function, is on the outside. Okay? Whereas previously it was always the inverse trig function on the inside. How does that change things? Well, first of all, if you analyze the inside expression, you'll recognize that object isn't an angle, right? Inverse trig functions produce angles, but this is the regular sine function, okay? Its input is an angle, 97 degrees, and the thing that it produces is basically a y-coordinate, technically y over r, but some kind of ratio of sides, or maybe it's y over r, okay? Now, I don't have a calculator in front of me, and if this were a test question, you wouldn't be allowed to have one. I don't know what the sine of 97 degrees is. Maybe I could figure out what the sine of 97 degrees is. It's some number, and then I could ask for the inverse sine of that. But that really doesn't work. We need the truth is this problem is doable completely conceptually. Okay, and here's what you have to think about. In the previous example, the inverse sine and the sine function canceled out. So here's kind of a question. Will they cancel out in the end here? In other words, will this just be equal to 97 degrees? You have to think about this very carefully. I mean, you would kind of expect it to be true, although there is a little bit of doubt, because I think I told you in a previous lesson that this so-called inverse sine function isn't truly the inverse of the sine function, as we're about to see. So here's the idea. The sine of 97 degrees, what is it? Well, let's draw a picture. I suppose I'm free to draw a circle of whatever radius I want. For convenience, I'll choose r equal to 1. All right. Now, 97 degrees is, just a little bit past 90. Okay. So that's 97 degrees. And the sine of 97 degrees is the y-coordinate of this intersection point. Technically, it's y over r, but since r is 1, it's just the y-coordinate. So the expression on the inside here, sine of 97, that's just the y-coordinate of this intersection point, right? Okay, now I don't know what it is, but whatever it is, it's just some number. Okay, it's the y-coordinate of this intersection point. Now, what am I doing with that number? I'm taking the inverse sine of it. Okay? Now, what does that do? Taking the inverse sine of this number will give you an angle whose sine is this number. Okay? If you didn't really follow that, temporarily just hide the expression in the parentheses to make things simpler. Sitting underneath my hand is some number, and I'm taking the inverse sine of that number. Okay? What that's going to do is it's going to produce an angle whose sine is the number underneath my hand. Okay? Now, if you think about it, the number underneath my hand is sine of 97. That's going to be the y-coordinate of this point. So certainly an angle whose y-coordinate is this number right here certainly would be 97 degrees. 97 degrees is an angle whose sine is the number sitting underneath my hand. The problem is that 97 degrees is not in the restricted range for sine. It isn't. Whatever number is sitting underneath my hand here, the inverse sine of that number cannot possibly be 97 degrees, because the restriction on the inverse sine function's range is in degrees. It's negative 90 to positive 90. Okay? So I don't care what this thing is. The inverse sine of a number cannot be 97 degrees. It has to be an angle between these two guys. Right? Ultimately, what that means is the inverse sine of this object has to be an angle whose sine is this number. In other words, whose y-coordinate is this y-coordinate. However, it has to be within this interval. So what angle would have the same y-coordinate as this point, but be within this interval? The answer is 83 degrees. Basically because 97 degrees is, 7 degrees more than 90. If you did 7 degrees less than 90, that would have the same y-coordinate. So this point right here, this angle, 83 degrees, will be an angle whose sine is that number right there, okay, which is what I want. However, 83 has the advantage of actually being within inside the restricted range. So the correct answer is 83 degrees. Extremely tricky and very surprising. This is demonstrating to you that the regular and so-called inverse sine functions, they're not really inverses. They're sort of like pseudo-inverses in a way. So yeah, in the homework, you'll sort of think a little carefully about when exactly the regular and the inverse sine function will cancel to like give you what you started with, or whether they'll give you something else. Okay.